We're at the airport. You know those moving walkways at the airport?
Yes.
Those moving walkways that carry you like, I don't know, like 30 meters. You got to walk like 2 kilometers to your gate, and they help you along maybe like 30 meters. I don't know, make you feel better. I think they're meant to entertain you more than anything else, right? You run backwards on it and whatever. But anyways, picture those moving walkways at the airport, okay? The moving walkway at the airport is moving to the right at 2 meters per second. Got it? So it's moving this way at 2 meters per second. If I stand on that moving walkway, how fast am I moving relative to, maybe there's a store over here, you know, that convenience store over there, which, by the way, I don't know if you ever noticed this, always seems to be in the middle of the moving walkway. So it's like you get on the moving walkway, and then you got to go back halfway, or you have to walk halfway, so it kind of defeats the purpose of the moving walkway. But anyways, there's a store right there. The moving walkway is moving at 2 meters per second relative to that store. So the store is not moving, obviously. The moving walkway is. You're standing on the moving walkway. You look at the store, and you can tell that you're moving at about 2 meters per second relative to the store. Does that make sense? But what if you get on that moving walkway and you decide, well, I want to go real faster. So I'm going to walk at 3 meters per second. Okay, I can walk right now on the ground, the non-moving ground, at 3 meters per second. How fast can I walk on a moving walkway? 3 meters per second. If I get on that moving walkway and walk at 3 meters per second, how fast am I going to be moving relative to this store that's halfway along that moving walkway? What's my speed relative to the store? 5 meters per second. You know, you've done that, right? You walk on a moving walkway, and man, it just feels like you're moving so fast relative to that store or that whatever over there, right? What if I get on that moving walkway and walk the other way? So it's moving at 2 meters per second to the east, and I decide I'm going to walk at 3 meters per second to the west. How fast am I moving relative to the store now? 1 meter per second, but the other way, right? How do we do that? How do we find the velocity of me on this moving walkway relative to the store? How did you do that? You guys told me the answer both times, right? When I said I'm moving 3 meters per second in the same direction as the moving walkway, you said, oh, you're moving 5 then relative to the store. What if I'm moving opposite? You told me I was moving 1 relative to the store in the opposite direction. How'd you do that? You added them together. Yeah, you added vectors together. When you want to analyze relative motion, the motion of one thing relative to another, we add vectors together. Now, what we're going to do today is do relative motion, but not relative motion where one thing is moving to the east and one thing is moving to the west, or both are moving to the east or both are moving to the west. We're going to do relative motion where one thing is moving to the east and one thing is moving to the north. The good news is we still do the same thing. We still add vectors together. But we don't add vectors together like 2 plus 3 is equal to 5. We add vectors together like 2 plus 3 is equal to, I don't know, the square root of 2 squared plus 3 squared. Make sense? We've been spending a couple days now adding vectors together, right? We're going to do that. We're going to continue to do that today, except we're going to do that in an application, the application of relative motion. Make sense? So instead of maybe on this moving walkway, moving at 2 meters per second, me walking at 3 meters per second. Let's say now maybe I'm walking at 3 meters per second. I'm walking at 3 meters per second, but there's a wind of 5 meters per second of 2 meters per second that's blowing on me. And let's assume there's no friction, so like whatever speed the wind wants to take me, the wind is going to take me, okay? Okay, so because I'm not restricted by friction between my feet and the ground. There's a wind of 2 meters per second. I'm going to end up moving at 5 meters per second, right? Right? We add these vectors together. What if, how about this one? What if I'm flying my airplane at 20 meters per second to the north? What if there's a wind of 10 meters per second to the east? How fast am I moving relative to the ground? Is this not the same question as the moving walkway question or the walking one way with the wind question? It's the same question, right? We add these vectors together. How do we add these vectors together? Redraw a right angle triangle. Now, these are my vectors, my component vectors that I have to add together. So I got to make sure that I draw these two vectors, 3 words, something to something, head to tail. I can do that in one of 2 ways. I can draw it 20 meters plus 10 meters per second, sorry, not meters, meters per second. Or I can draw it 10 meters per second plus 20 meters per second. It doesn't matter which one I add first. Add the wind, add the way that I'm aiming or heading. Doesn't really matter which one I add first. In the end, my resultant vector here, I'm going to draw this as a dotted line vector just to distinguish it more. Okay, that's my resultant vector. That is the sum of the vectors. That's my relative velocity, the velocity of my airplane relative to the ground. You can imagine if you're flying, you're aiming directly north to Edmonton, and there's a wind that's blowing to the east, and you're not compensating for that. Where are you going to end up? Not in Edmonton, right? Somewhere like, I don't know, Lloydminster? Well, that would have to be quite a wind, I guess, but if you ended up in Lloydminster. But you know what I mean, right? You end up east of Edmonton, right? You guys ever notice this? How many people drive here? Okay. You've driven in a strong wind? Like yesterday was a strong wind, right? Driving towards Calgary, let's say that wind usually blows from the west to the east, a Chinook wind. Okay, let's say it's blowing at, I don't know, 30 meters per second. That's pretty strong, but sometimes it is blowing at 30 meters per second, those really, really strong Chinook winds. Let's say you're going at, you want to go directly north. You want to go directly north. In other words, you have to aim some other direction to go directly north, right? Something plus 30 is equal to my directly north, my resultant vector. Does that make sense? This is the resultant vector, so in this case we'd say whatever direction I aim, this one, I aim this way, and then 30 meters per second wind this way allows me to go, my resultant vector, the sum of the vectors directly north. Does that make sense? You ever notice that when you're driving your car in that strong wind? Where's your steering wheel? Right? Your steering wheel's over here. You're aiming somewhere over towards, like, I don't know, Bragg Creek in order to end up going directly north, right? Because that vector that's aiming towards Bragg Creek plus the east wind ends up, those two vectors added together, ends up giving you a velocity relative to the ground, which is what you want, of directly north towards Calgary. Make sense? Okay, so you can see in the examples that I've given you that I've got 2 types of vectors here, these solid line vectors and dotted line vectors. These solid line vectors, where is it here? That's not what I'm... These solid line vectors are the vectors that contribute to where I go. Think about that again. Okay, think about that. I aimed, in that first example, I aimed directly north. That was a solid line vector, right? Does that contribute to where I go? Where I aim, does that contribute to where I go? Of course it does, right? But there was also a wind to the east. Did that contribute to where I went? Yes, the wind contributed to where I went. That's a solid line vector. Now, where I actually go is the dotted line vector. That's the sum of the solid line vectors. The sum of the contributing vectors is my dotted line vector. In the second example, I aimed towards Bragg Creek. That was a solid line vector, right? Why? Because that contributed to where I went. But there was a wind blowing to the east. That was also a solid line vector because that contributed to where I went. When I added those 2 solid line vectors together, what did I get? That dotted line vector that was directly north, where I actually went. My velocity relative to the Earth. Does that make sense? So I'm gonna draw a little table here. Solid line vectors and dotted line vectors. And we'll give you a few examples of what we might see as a solid line vector or in a dotted line vector. My solid line vectors, remember, are vectors that contribute to the motion, to the actual motion, I should say. And my dotted line vectors are the actual motion, or the motion relative to something, relative to the earth, relative to the ground, whatever. Does that make sense? I'll also put in brackets here beside the dotted line vectors, this is the resultant vector. The sum of all the vectors. So what type of term might we see as a dotted line vector in some of these problems involving, say, airplanes or boats or whatever? In other words, what type of vectors contribute to actual motion? Well, if you're flying in an airplane, where you aim or where you head contributes to your actual motion, right? Where I aim is not where I end up going, not always at least. Where I aim contributes to where I actually go. Where I head isn't where I'm going. Where I head contributes to where I actually go. Good? If we're talking about airplanes, you ever, when you're flying in an airplane, look at the back of the little magazine, the in-flight magazine that's in the seat in front of you? At the back of the airplane, in the back of the magazine, they usually list the different planes that this airline flies. You ever notice that? They'll give you like different statistics about those airplanes, including wingspan and length and how many passengers it carries and the airspeed. They'll say the airspeed of it. Like they might say the airspeed of an airplane. Oops, can't spell airspeed. Doesn't sound like that hard of a word to spell. The airspeed of an airplane might be 900 kilometers per hour. That means in the absence of a wind, it can travel at 900 kilometers per hour, right? Well, that's not how fast it actually goes, because if there's a tailwind, maybe it goes at 930. If there's a headwind, maybe it goes at 860, right? But that 900 kilometer per hour airspeed contributes to how fast the airplane actually goes, right? What else contributes to how fast an airplane goes? A wind. A wind speed. Now, if a plane can go 900 kilometers per hour in still air, but there's a wind speed of 50, or maybe it can only go 850, or maybe it can go 950 if it's a tailwind. If we switch this kind of argument to boats, maybe, and rivers, maybe there's a river current. Try to swim across a river, like directly east. I'm going directly east across the river. I'm swimming directly east, but there's a current going downstream. Where do I end up? Well, somewhere downstream, right? Where I aimed directly east contributed to where I ended up, but the river current also contributed to where I ended up. When I add those two vectors together, I get my actual velocity. I'm going to say my dotted lines, the resultant, the actual motion. What's my actual velocity? What's my velocity relative to the earth, relative to the ground, relative to whatever. So basically, if it contributes to the motion, you're going to add the vectors together as solid line vectors. If you're looking for, or if you have the actual motion, it's a dotted line vector, it's the resultant vector, it is the sum of the vectors. Okay, I promise you, when we go to do questions, this is actually not going to seem too challenging for you, okay? What we've done already with vector addition is harder than what we're about to do today. Let's do an example. Example number 17, it says the captain of a ship aims the ship due north at a speed of 10 meters per second. current in the ocean of 2 meters per second to the west carries the ship off course. What's the ship's resultant velocity? I should have added that in as another dotted line vector. The resultant velocity. Captain of a ship aims his ship due north. Is that a solid or dotted line vector? Does that contribute to where the ship goes, or is that where the ship goes? Brett, what is that? Does that contribute to where the ship goes, or does the ship actually go due north at 10 meters per second? That contributes. So that would be a solid or dotted. That would be a solid line vector. So let's draw that right now as a solid line vector. 10 meters per second to the north. Solid line vector. There's a current of 2 meters per second to the west. Does that contribute, Molly, does that contribute to where the ship goes? Or is that where the ship goes? Does the ship actually go west, or does that just contribute to where the ship goes? Yeah, it just contributes to where the ship goes. So we're going to make that a solid line vector as well, right? And I'm going to draw that like this. 2.0 meters per second. Now, these are solid line vectors that both contribute to where the ship goes, so I have to add these together. When I'm adding vectors together, I always need to draw them blank to blank, head to tail. So I'm going to draw these two vectors head to tail. Now I've got a couple of options. I could draw it like this. Is that okay? Is that valid? Yeah, they're drawn head to tail. The other option I could have done is I could have drawn it like this. Is that okay? Yeah, either one of those would be okay, right? We're going to get the same hypotenuse here. We get a different angle, but we're just measuring our angle from a different reference point. I'll go with the blue here, but the green would have worked as well. My resultant vector, my dotted line vector, which is my actual motion, or my motion relative to the shore, is the sum of these vectors, which is always drawn from, this isn't new, it's always drawn from start to finish, right? The resultant vector always drawn from start to finish. So I'm going to label that R. You might want to label that V. Up until today, it's been displacement vectors we're adding. We're adding velocity vectors here today, whatever. Same process. Let's label the angle right here. Let's find the value of R. This is easy, right? We already got a right angle triangle. In fact, most of these questions would be like this. Unless you have like multiple things that are contributing to the motion, it's almost always going to work out to be a right angle triangle right off the top. So we're going to say for this, the square root of 2 squared plus 10 squared gives me 10.1, or it actually rounds to 10. And my angle, theta, drawn at the start, is the inverse tan of opposite over adjacent. That would be, what is it, 10 over 2 or 2 over 10? 2 over 10. So theta would be, I expect to get a pretty small number there. What do we get? 11 degrees, yeah. So 11 degrees what of what? I'm heading to the north, but there's a current that goes to the west. So I'm going to end up north and west somewhere, right? But is it 11 degrees north of west? Or is it 11 degrees west of north? Yeah, look at where I'm measuring the angle from. I'm measuring it from the north, of north. West from north, west of north. You can imagine how if you're the captain of a ship, knowing a little bit of vector analysis might be a valuable thing, because it might be useful for you to predict where you're going to end up, or at least be able to predict where you should aim in order to end up where you want to end up. You can imagine as a pilot that might be a useful skill as well. Does this make sense? Okay, I'd like you to take a look at your worksheet right now. It is worksheet number 8. Right now, I'd like you to do the first 4 questions on worksheet number 8. First 4 questions on worksheet number 8. We'll give you a few minutes to work on those in class. Then we'll do one more example, and we'll leave you with a couple questions for homework. Let's finish it off with one more example, number 18. So it says, a boat heads north across a river at 10 meters per second. It's flowing east at 5 meters per second. The river, by the way, should be, I should have had a width of the river. I'm not sure on your example if it says the width of the river or not. Does it? No. The width of the river is going to be 200 meters wide. Got it? What's the boat's velocity relative to the shore? How much time does it take the boat to cross the river? And C is, how far downstream does the boat end up when it makes it to the other side of the river? Let's draw the river here. The river is flowing east. So that's going to be a solid line vector, right? Because that contributes to where the boat goes. Clearly, the river current is going to contribute to where the boat goes. So let's draw that as a solid line vector to the east. And that's going to be 5.0. Now, the boat heads directly north across the river. Does that contribute to where the boat goes? Yeah, where you head or where you aim certainly contributes to where the boat goes. So we're going to add those 2 solid line vectors together in order to get the velocity of the boat relative to the shore. In other words, in order to get the dotted line vector, the resultant vector. Hey, this is just the same as questions 1 through 4 on the worksheet that you've already done, right? Let's find the value of R here, the magnitude of it. We're going to say it's the square root of 5 squared plus 10 squared. That gives me a value of 11.1803. Or we're going to round that to 11 meters per second. And theta would be the inverse tan function of 5 over 10. .565, or 20. We're on that to 27 degrees, and that would be west of north. 27 degrees west of north. You could have drawn it differently, right? You could have drawn the 5, then the 10, and then you would have gotten 63 degrees north of west. That would be fine. Good. East of north, yes. Thank you. Good. Just the same as questions 1 through 4, right? Now, this is the challenge question. It'll be, how long does it take for the boat to cross the river? How long does it take for the boat to cross the river? Any ideas? Knowing that the river is 200 meters wide, which, by the way, notice I did not include with my vector diagram. That's just separate, right? I can't add 200 meters to 10 meters per second. Those are 2 different things. I add velocity to velocity. The displacement is just a separate thing. Any ideas here? Almost. Okay, Corey said basically, let's say V is equal to delta D over delta T. Let's rearrange that. Delta T is equal to delta D over V. And Corey said, let's take the 200 meters and divide it by the 11 meters per second. But we can't do quite that. Because whenever we use this equation, pay really close attention to this. Whenever we use this equation, the velocity and the displacement are always in the same direction. My displacement is straight across the river, but my velocity at 11 meters per second is at an angle of 27 degrees. Does that make sense? We can't use the 11 and the 200 together because they're in different directions. So what do you think you're going to do? I'm going to use the 200 meters, but what velocity do I need to use? The 10 meters per second. that make sense? If I'm using a y displacement, I need to use a y velocity. I could use the 11 meters per second. I could. Corey, if I use the 11 meters per second, I would just have to find a displacement in that direction as well. And I'd end up getting the same answer. It would just be harder to do that. So I'm going to say, look, I know the y displacement. I know the y velocity. Divide the two, and I get 20.0 seconds. That's how long it takes to go across the river, 20 seconds. Now see how far downstream does the boat end up when it makes it to the other side. We're going to use the same equation for that, displacement divided by time, but this time we're going to rearrange it to solve for displacement. What velocity? If I want to find out how far downstream it ends up, right? If I want to find out this displacement like this way, how far downstream it ends up, the horizontal displacement, what velocity am I going to use? 10, 11, 5? 5, right? Hold on for a second, guys. Hold on. 5 meters per, but what time do I use? Oh, 20, no, wait a second. Wasn't that 20 seconds the vertical time? The y time? Time is a scalar, right? Velocity has to be consistent with displacement in terms of direction, but time's a scalar, right? So there is no x and y time. If it was 20 seconds for the y, it's 20 seconds for the x as well. 5 times 20 is going to give me 100 meters. So I end up 100 meters downstream. Does that make sense? All right. We'll do this. We'll do the question number 5 tomorrow in class on this. Just your homework, guys, is what do we got here? Quiz number 7, which is the fake quiz we did today. And then I posted just a second ago fake quiz number 8 that I want you to do for homework, okay? So fake quiz number 8 and quiz number 7. That's the homework for tonight. Have a good night, everyone.